Hello everyone, let's do now the practice problems for chapter 13, and from here you can see that we have a very good question about converting from Celsius to Fahrenheit. So to do this problem, we need to use this equation that you can see right here. So T Celsius is equal to T Fahrenheit minus 32 times 5/9. Okay, so when you substitute T Fahrenheit with 77, so we'll have here 77 minus 32, and then you multiply by 5/9, and when you do the calculations, that's going to give you 25 Celsius. So C is the right answer here. And what is the Kelvin equivalent for minus 40? So when we do conversion from Celsius to Kelvin, we add 273.15 to Celsius. That means we have minus 40 plus 273.15, and you will see that's equal to 233.15 Kelvin. So this is how can we convert from Celsius to Kelvin. Okay, now if we come to number 3, so number 3 looks a little bit complicated, but it's not that complicated. We need to use this equation, which is change in length is equal to the original length times alpha, which is the coefficient of linear expansion, times change in temperature. So the problem here is asking about the change in length. Okay, we have the original length, which is 1 meter. We have the change in temperature. So the temperature was 20 and it became 120, and it became 120. So and the coefficient of linear expansion for steel is equal to 1.2 times 10 to the power minus 5 Celsius inverse. So now we can do the following. So change in length is equal to 1 meter times 1.2 times 10 to the power minus 5 Celsius inverse times change in temperature, which is 120 minus 20, so that's going to give me 100 Celsius. Okay, and that's going to give you here 120 times 10 to the power minus 5 meters, which is equal to B, which is 0.0012 meters. Okay, so this is number 3. So number 4, the same idea. So this is a thermal expansion, but instead of linear expansion, we have now volume expansion. So we need to use this equation. Delta V is equal to V0 times beta, coefficient of volume expansion, times delta T, change in temperature, from 20 to 70. Beta for glass is equal to 27 times 10 to the power minus 6 Celsius inverse. So now you will see that delta V is equal to the original volume, which is 1 liter, times beta 27 times 10 to the power minus 6, and then times change in temperature. So change in temperature is 70 minus 20, so you will have here 50 Celsius. Do simple calculations. So we have 1 times 27, so we have 27 times 50, that's equal to, do that again. So I have 27 times 50, so that's equal to, and then we divide the whole equation by 1 million. and that's going to give me 0.00135, which is 0.0014. So B is the right answer. So we have change in volume is equal to 0.0014 liters. Okay, these two examples are very important. Let's now jump to the next example, which is number 5. For number 5, guys, this problem is talking about the thermal equilibrium. So we have two different materials here. So we have copper and we have water. So the water and the copper have different temperatures. So the copper has 100 Celsius as a temperature, and the water has 20 Celsius as a temperature. And then they are gonna be like one system, and after the equilibrium they will achieve the same final temperature. So now we can benefit from the heat for system 1 is equal to the heat for system number 2. So we'll do the mass of the copper, the specific heat for the copper times change in temperature for the copper. That's equal to the mass of water, the specific heat of water, times the change in temperature for water. Okay, let's rewrite this equation. So we have the mass of copper, I have the specific heat for copper, and I have here 100 Celsius for copper minus the equilibrium temperature, and that's equal to the mass of water, the specific heat of water, and then we have the equilibrium temperature minus 20 Celsius, and here we have like 100 Celsius. Let's multiply MC C sub C inside the parentheses and MW CW inside the parentheses and see what will happen. So that's going to give me the mass of the copper, the specific heat of the copper times 100 Celsius, and then minus the mass of the copper, the specific heat of the copper times the equilibrium temperature for the system, and that's equal to the mass of the water, the specific heat of the water times the equilibrium temperature for the water, and then minus the mass of the water, the specific heat of the water times 20 Celsius. So that's very good. Let's have now some numbers. I know the mass of the copper and also I know the mass of the water. So I do like 100 gram times specific heat for copper. The specific heat for the copper actually was written right here. So for the copper I have 0.39 joule per gram Celsius, and for the water I have specific heat is equal to 4.18 joule per gram Celsius. So let's use these numbers right here. So I can have here 0.39, and I have joule per gram Celsius, and I multiply that by 100 Celsius, and then minus the mass of the copper, which is 100 grams, times 0.39 joule per gram Celsius, and then multiplied by the equilibrium temperature, which is right here. And that's equal to the mass of the water, which is 200 grams, times the specific heat of the water, which is 4.18 joule per gram Celsius, and then we multiply that by the equilibrium temperature for the water, and then minus the mass of the water again, which is 200 Celsius, multiplied by the specific heat of the water, 4.18 joule per gram Celsius, and then multiplied by 20 Celsius. That's great. So let's do now some calculations here. So 100 and 0.39, I believe. So 100 and 100, so So I believe that's going to give me like 3,900. Yes. So we have from here, we have 3,900, and from here we have minus 39 times t from here, and from here I think we have something around let's see, I will bring the calculator, so that's going to give me the exact number. So I have 200 times 4.18. Let's do that. 200 times 4.18, so that's equal to 836. I'm going to write that down. So I have 836, so 836 times t, and then minus, I have here 200 times 4.18 times 20. So just bring the calculator here and do the following. So I do 200 times 200 times 4.18 times 20, so that's equal to 16,720. So I have 16,720. Okay, now let's solve for temperature. I have now 3,900 plus 16,720, that's equal to 39 times t plus 836 times t. Now when I solve, I will bring the calculator. Now when I solve for temperature, I divide 3,900 plus 16,720 divided by 39 plus 836. So let's add here 3,900, so that's equal to 20,620, and then I divide the whole number by 39 plus 836, and that's equal to, so you can see now, guys, the answer is 23.56, and that's going to give me 23.6. So this is for problem number 5. Okay, maybe problem number 5 needs some work, but if you follow this solution, you will do pretty good, okay, with problems like this. So what I'm going to do, I'm going to erase the whole thing and then move to problem number 6. So problem number 6 is asking about what is the root mean speed of oxygen molecule at 300 Kelvin. I know that the molecular weight for the oxygen molecule is 0.032 kilogram per mole. Okay, so let's now see the V root mean square. So the V root mean square, guys, V root mean square, it's equal to square root of 3 times R. So R here is the gas constant, and then times temperature, and we divide the whole equation by capital M. Capital M is the molecular weight. So that's equal to, I have square root here, so 3 times, I need to figure out the gas constant. I already have the gas constant right here. Okay, so the gas constant is 8.318. So we have 3.8 8.314. I'm sorry. So square root times 8 0.314, and then times the temperature, which is 300 Kelvin, and we divide then the whole equation by the molecular weight, which is 0.032. Okay, I will double check the units of the gas constant. Actually, we can get the units from here. We know from the ideal gas equation that pressure times volume is equal to number of moles times R, the gas constant, times temperature. So then we can get the units of the gas constant. So we have PV over NT. So that's going to give me here pressure, which is Newton over meter squared, and volume meter cubed, and we divide the whole thing by number of moles and then Kelvin. Okay, yeah, so we will have a Newton meter per mole Kelvin. Newton meter per mole Kelvin. Okay, so this is the unit. This is the unit of the gas constant. But since we are following this equation, I think it's a very good idea to write the square root right here, including these units. So what I'm going to do here, I'm going to write like a big square root, and maybe that's going to help you guys to work better with units. So you have 3 times 8.314. I have Newton per meter squared, per meter cubed. Okay, and then the whole thing per mole Kelvin, and then we multiply the whole thing by 300 Kelvin, and then we divide by 0.032 kilogram per mole. Okay, so that's great. Now let's now multiply all of these numbers together and then focus on the units and see how can we do with the units. Okay, so I'm going to multiply all of these numbers together. This is the calculator, it is right here. So I have 3 times 8.314 times, so that's okay, we have 3 times 8.314 times 300, so that's equal to, and then we divide that by 0.032, so that's equal to, and then we have the square root. So before I write the square root, so let's write this number. So the result from here is 2,3,831.25 under the square root. Okay, so let's now have the square root. So the square root for this number gave me 400. Let's see, it gave me 483. 483, which is C. So that's right. So that's right. So C is the right answer. And now we need to double check and see how can we work with these units. Also the units, guys, are under the square root. So what I have here, I have Newton per meter squared. So meter squared will be cancelled with one of those 3 meters. So I will end up with Newton, which is kilogram meter per second squared times meter, okay, and then times the temperature Kelvin, which is from here, and then I divide the whole thing by kilogram per mole. Okay, so kilogram per mole. I have here mole Kelvin. So this Kelvin will be cancelled with this Kelvin. And this mole right here will be cancelled with this mole right here. So this Kelvin right here was already cancelled. Okay. And the kilogram from here will be cancelled with kilogram from here. We will end up with meter squared over second squared, square root meter squared over second squared, and that's going to give me here meter per second, which is the velocity units. Okay, so I already cancelled this mole with this mole, this Kelvin with this Kelvin. 2 meters from here, meter squared from here with meter squared from here. So I just end up with 1 meter with just meter here, which is what we have right here. Okay, Newton is kilogram meter per second squared. Okay, so, and also you can see that the gram will be cancelled with the gram right here, and it will end up with the square root meter squared over second squared. Okay. Yes, I think that that looks clear. You can go through the recording more than one time, so you can see what I did with the units, guys. Okay, so I'm going to erase the whole thing and then move to the next problem. So the next problem is asking about the average kinetic energy per molecule at 300 Kelvin. We know, guys, at certain temperature the average kinetic energy is proportional to temperature. So we can do average kinetic energy is equal to 3/2 Boltzmann constant times temperature. So I have 3/2 times Boltzmann. So Boltzmann constant, it was written right here. So it's 1.38. So Boltzmann constant, which is right here, it's 1.38 times 10 to the power minus 23, and we multiply that by temperature, so you have 300. The unit of a Boltzmann constant, it is joule per Kelvin. You can see that you have the temperature here with Kelvin, so you can see now that the answer will end up with the joule unit. So let's come here, and I will multiply 3 divided by 2. So I need to do here, I need to refresh the calculator. So 3 divided by 2, the 3 degrees of freedom, and then I multiply that by 1.38, and then I multiply that by 300, so that's equal to, I have here 621 times 10 to the power minus 23 joule. Okay, or in other words, we have 6.21 times 10 to the power 21 joule. Let's double check here. So Boltzmann constant should be with a positive sign. So this is positive, that was a typo, and this is positive. So we have positive 10 to the power positive 21. Okay, so that's right. So Boltzmann constant is equal to 1.38 times 10 to the power 23 joule per Kelvin. Okay. Okay, so sorry for the typo. We did fix the typo right now. We know that we have positive sign here. Okay, that's great. Let's now move to problem number 8. So for problem number 8, so 1 mole of gas at 22.4 liter has 1.01 times 10 to the power minus 5 Pascal and 273 Kelvin. So what is R? So R here is the gas constant. Yeah, simply here you need to use the equation of the ideal gas to figure out the gas constant. So we are using like PV is equal to nRT. Okay, so standard temperature and pressure for 1 mole of gas. Okay, so we'll see that R is equal to PV divided by NT. So we will have pressure as 1.01 times 10 to the power 5 Pascal times volume, which is 22.4 liter, and then we divide the whole thing by 1 mole and divide also by 273 Kelvin. So that's going to give me R is equal to, which is the gas constant, So let's do that. I have 1.01 times 22.4, that's equal to, and then I divide by 273, so that's equal to, and then I multiply this equation by 10 to the power 5. So that gave me 8,287. Okay, let's see the units here. Let's see the units and then compare. So I have Pascal, I have here liter, mole Kelvin. Let's look at the units first. So I have liter and I have Pascal, okay, and I have here mole Kelvin. So before I write the number, let's work with units. So I have Pascal, liter over mole Kelvin. So the mole Kelvin that we have right here is right here, so that's right. We have here Pascal liter. So the liter is the volume and Pascal is pressure. So maybe I need to come here and do some work. So Pascal actually is Newton over meter squared times liter. So let's look at the liter. I know that 1 liter is equal to 1 decimeter. Okay, 1 decimeter cubed, that's right. And 1 liter is equal to, so DC means 10 to the power minus 1. If I cube it, so that's going to give me here 10 to the power minus 3 meter. Okay, so that means, guys, from these units right here, I have Pascal, which is Newton over meter squared, and then I have liter, which is 10 to the power minus 3 meter, and then we divide the whole thing by mole Kelvin. Sorry, meter cubed here. That's great. So we cancel meter squared with meter squared from here, so we have just 1 meter. And we know that Newton actually, I will write it right here, or maybe right here. So Newton actually is kilogram meter per second squared. That's right. But we have kilogram meter per second squared times meter, so that's going to give me here kilogram meter squared per second squared, and then divided by mole Kelvin. Now, who can tell me what is this? So kilogram meter squared per second squared. Okay, this is mass times velocity squared. And if we go to the kinetic energy equation, which is 1/2 mass times velocity squared, so this is the kinetic energy equation. We have kilogram mass, and we have meter squared over second squared. So this is going to give me here joule, which is the unit of the kinetic energy. Now you can see the whole thing here will be converted to joule, but we need to multiply this by 10 to the power minus 3. Okay, let's now have what we have in the calculator. We have 8,287. So we have here 8,287 times 10 to the power minus 3. That means we have 8.287 joule per mole Kelvin. Okay, which is exactly 8. Oh, it looks like A is the right answer. So we have 8.28, which is 8.3. So A is the right answer. Okay, you can see how understanding the unit can help you to do better work from this simple example. Okay, I'm going to move quickly to problem number 9. And in problem number 9, we have at 300 Kelvin, what is the ratio of root mean square speed of helium, which has molecular weight 4 gram per mole, to oxygen, which has 32 gram per mole as molecular weight. Okay, so we know that the root mean square equation actually speed, the root mean square speed is equal to 3 times gas constant times temperature, and I believe times Planck's constant, I believe so, times Planck's constant, I will double check, and then divided by the molecular weight, but I will double check here. So anyway, so for now, let's keep it R, but double check. So double check. Let's do this simple work. Let's do the simple work here to make sure if it is R or Planck constant. So I know that I have like 3/2 from thermal kinetic energy. I have 3/2. So I will rotate this a little bit. Okay. So I have 3/2 times Boltzmann constant times temperature. So that's equal to the average kinetic energy. I have 1/2 times mass times velocity squared. Okay. So now the half will be cancelled with half, and I will end up with Boltzmann constant times temperature, and that's equal to the mass times velocity squared. And we will have here 3k Boltzmann times temperature is equal to the mass is equal to the mass times velocity squared. Okay, so now we do v squared is equal to 3 times k Boltzmann times temperature divided by the mass, or we can do v is equal to the square root of 3k Boltzmann times temperature divided by the mass. Okay, so now we can see that if I use the mass, and in the denominator, I need to use the Planck's constant. If I'm using the molecular mass, I need to use here the gas constant. Okay, so now I have two v root mean squares. I have one of them for helium, and I have another one for oxygen. Okay, so for helium I have square root of 3RT divided by m helium, and for oxygen I have square root 3RT divided by the mass of the oxygen. So if I get the ratio, I need to divide the V oxygen divided by the V helium, and that's going to give me the square root of 3RT divided by the molecular mass of the oxygen, and I divide the whole thing by the square root of 3RT divided by the mass of the helium. So we'll see now the ratio, guys, actually is between root mean velocities and molecular masses. So I will have here V oxygen over V helium. That's equal to square root of, so let's see here, I have 1 over molecular weight of oxygen. So I have here molecular weight for helium divided by molecular weight of oxygen. Okay, so just have numbers, and I have like the molecular weight for helium is 4. The units will be cancelled, of course, and the molecular weight for oxygen is 32. Okay, so now if I have the calculator right here, so I multiply this by 0, so that's going to refresh my calculator. So I divide 4 by 32, that's equal to, and then I get the square root. That's going to give me 0.35. Okay, 0.35. But let's see the ratio itself here. So what is the ratio of root mean square speeds of helium to oxygen? So I think we need to divide. So the oxygen is 32 root mean square speed. So what's the ratio of root mean square speed of helium to oxygen? If I flip, helium to oxygen, look at, I did here oxygen to helium. So just I need to flip this equation. So I do 2.8. Let's redo the calculations again. Let's redo the calculations again. So I have here 32 divided by 4, that's equal to, and then I get the square root. That means we have square root of 8. So square root of 8 is the right answer here. Okay, so the thing that you need to do here, just you need to flip. You need to have the v root mean square for helium divided by the v root mean square for oxygen, and that's going to give you the square root of 32 divided by 4. So yeah, so that's going to give you the square root of 8, which is the right answer. Okay, so what I did right here, I just did the ratio between the root mean square speed of oxygen divided by the root mean square speed for helium. So that give me the wrong answer. But if you flip them, if you do v root mean square for helium divided by v root mean square for oxygen, so that's going to give you the right answer. So that's very good. Let's now move to the next question. So what I'm going to do right now, I'm going to do the following here. Move to question number 10. And in question number 10, I have, which equation relates gas pressure to molecular motion? This is the equation, guys. This is the equation that relates gas pressure to molecular motion. So we have like around 20 problems, and what I'm going to do, I'm going to create another recording for you. So this is the first recording from the practice problems for chapter 13, and I'm going to create another one for you. So yeah, see you in the second part of the practice problems from chapter 13.